Channels like this don't last without people who care. We're 72 members into a goal of 200. If you're one of them, Patreon link below.
There is something that happens right before sleep, when the body is still but the mind hasn't quite let go yet. A kind of loose attention. The room gets larger somehow. Not because anything changed, but because you stopped filling the space with intention. You're just there in the dark and the dark gets roomy. That feeling. Hold it for a moment. The Sleepy Physicist is self-funded, and it runs because some people choose to make it run. We are close to 200 members on Patreon, and that number matters, because 200 is the point where this channel stops feeling fragile. For everyone who supports, I build extra things alongside these episodes, things like detailed explorations of what really happened when the dinosaurs went extinct, biographies of physicists whose names you know, and physicists whose names were nearly lost, and long reads for people who want to go deeper. If that sounds like something you want to be part of, the Patreon link is in the description. Pull a blanket up. The weight of it is specific, isn't it? Not just heavy, but a particular kind of heavy. The kind that presses you down into where you're lying without demanding anything back. You don't have to go anywhere. Tonight we're going to spend some time between the galaxies. Most people, if you ask them what the space between galaxies is like, would say something like empty, cold, dark. Maybe they'd add silent if they were being poetic. But it's not a wrong answer exactly. It just turns out to be incomplete in a way that changes almost everything. The picture most of us carry around is something like this. Galaxies are the islands, the light, the heat, the story, and between them nothing. A formless dark, the kind of emptiness you'd expect in a universe that's been expanding for nearly 14 billion years. Stretching thinner and thinner until the space between things is just space. Passive. Inert. A background. I used to think of it that way too. But here's what nobody told me, and maybe nobody told you either. The space between galaxies is not cold. It's not quietly resting. It is, in the most physically literal sense, searing. And I don't mean warm in the way that sounds like a metaphor. I mean temperatures that make the surface of the sun look like something you could hold your hand near. The stuff out there between the galaxies, in the filaments and threads that connect them across the most enormous distances we can imagine, is a plasma. Ionized, churning, electromagnetically agitated matter. And it runs, depending on where you sample it, from 100,000 degrees to 10 million degrees Kelvin. The sun's surface is about 5,773 Kelvin. Think about that. Here's the thing that took me a while to settle into. Space is not one thing. We say outer space like it's a single environment, a uniform medium you'd pass through if you travelled far enough from Earth. But it isn't. Interplanetary space, the thin stream of charged particles the sun breathes out, is different from interstellar space, the gas and dust between stars in a galaxy. And interstellar space is completely different from what waits between the galaxies themselves. The distances between galaxies are hard, not metaphorically hard, genuinely hard to process. Our nearest large galactic neighbour Andromeda sits about 2.5 million light-years away. The Milky Way and Andromeda are, by cosmic standards, close, practically touching. Between them, and between most galaxy pairs, the density of matter drops to something like 1 hydrogen ion per cubic meter. Sometimes less. The deepest voids reach densities 100 times below that. For comparison, the air in this room right now, while you're lying there, contains something in the neighbourhood of 10 followed by 25 zeros of molecules per cubic meter. The best vacuum a laboratory on Earth has ever produced still has trillions of particles per cubic meter. The best vacuum ever made by humans with machines. And the intergalactic medium is still emptier than that, so the empty part isn't wrong. The density is extraordinary. The sparseness is real. 1 particle per cubic meter drifting. Not nothing, but not much. You travel enormous distances, light years across, without a meaningful collision. The stuff out there is genuinely impressively thin, but thin and cold are not the same thing, and this is where most intuitions break down, including, I'll admit, mine. When I imagine gas that sparse, I imagine it cold, and it seems right somehow. Less stuff, less heat, temperatures drifting toward the background temperature of the universe, which is about 2.7 Kelvin, the afterglow of the Big Bang still cooling in every direction. That's cold. That's cold in a way that makes the Antarctic winter sound like a suggestion. And you'd think, if you had gas that thin, spread across the enormous spaces between galaxies, that it would just settle there, cooling toward that floor, drifting through the expansion of space with whatever energy it had left slowly bleeding away. You'd think it would be quiet. It isn't. Is it really possible that the emptiest regions of the observable universe are simultaneously among its hottest? The answer, as far as we can tell, is yes. Approximately yes. Not uniformly, not everywhere at once, but in the great glowing strands that thread the cosmos together, the temperature of the gas is genuinely, measurably, staggeringly high. And there's a reason for it. There's a mechanism, specific and physical, and actually quite elegant once you see it. The universe has been doing something to that gas, has been doing it for billions of years, not heating it from the outside, not pumping energy into it from some central source. Something much more inherent than that. Something to do with the way matter falls. The intergalactic medium, the gas out there between the galaxies, contains somewhere around half of all the ordinary matter in the observable universe. Not dark matter, not dark energy, ordinary baryonic matter. Protons and electrons, atoms, or what's left of them once they've been stripped down by the conditions they live in. Roughly half of everything you could build a planet from or breathe or hold is not in stars, not in galaxies, not in the dust clouds where new stars are forming. It's out there, in the space between, and for a long time we couldn't find it. The counts kept coming up short. The baryon census, when astronomers tried to add up all the ordinary matter they could observe in the local universe, fell 30 to 40% below what the physics of the early universe said should be there. This was embarrassing in the way that losing half of something is embarrassing. The matter wasn't gone. It was hiding. Hiding not in darkness exactly, but it's in a kind of thermal invisibility. Too hot to show up one way, too cool and too sparse to show up another. Sitting in the middle of two detection windows, glowing faintly in a frequency range that took decades of instrument development to access. We couldn't see it because of what it was, and what it was hot. The chapter ahead, I realise, is going to have to start where this one can't quite finish. There's a mechanism behind this, something clean and physical and almost obvious once it's laid out. The universe didn't heat this gas arbitrarily. It did it through one of the oldest forces it has, something it's been using since the beginning to pull matter together, to concentrate and compress and accelerate. Gravity. The void isn't empty, it's just been mistaken for one. There is a way that large things resist being pictured. Not because they're complicated, but because the mind keeps trying to place them inside something familiar, some room or field or sky it already knows, and they don't fit. They simply don't fit. The universe at its largest scales is like that. You can read the numbers, hold them for a moment, and still feel nothing click into place. That might be fine. The map doesn't require the territory to feel real. It only requires that you know where things are. So here is where things are. At the largest scale, we can meaningfully describe the observable universe organizes itself into a structure that nobody expected before the simulation showed it and the observations confirmed it. It is sometimes called the cosmic web, and the name is accurate in a way that names rarely are. It looks like a web. Not metaphorically. When you render the distribution of matter across hundreds of millions of light years, what comes back is a lattice of filaments and nodes and voids that carries a genuinely eerie resemblance to the threads a spider leaves between two branches after rain. The resemblance is a coincidence. There is no deeper meaning in it. But it is there, and it does make the structure easier to hold in the mind, so it's worth keeping. The web has 4 components: filaments, nodes, walls, and voids. Each one distinct, each one enormous, and each one playing a specific role in the architecture of everything we can observe. Filaments are the threads. They are elongated structures of matter, gas and dark matter predominantly, that stretch between the denser concentrations at their ends. They are not uniform. They taper and thicken along their length. They curve, they branch occasionally, they vary in density from their outer edges inward toward a denser core. But they are unmistakably linear. Stretched things, things that have a direction. Their lengths are the part that takes a moment to absorb. A typical cosmic filament runs somewhere between 500 and 800 million light-years. The longer ones push past that. Some extend to lengths approaching 1 billion light-years or beyond, though the boundaries of any individual filament become harder to define the longer it gets, the edges blurring into other structures, other concentrations, other threads. Still, 500 million light-years, 800 million. The Milky Way, our galaxy, is roughly 100,000 light-years across. A single cosmic filament is, at minimum, 5,000 Milky Ways laid end to end. They are the largest structures known to exist in the universe. Their diameter is narrower than their length by a large ratio. But narrower is a relative term here. A typical filament cross-section runs somewhere between 2 and 5 megaparsecs, which translates to roughly 6 to 15 million light-years. Wide enough that thousands of galaxies can sit inside one filament's width, arranged along its length and clustered toward its spine. At the intersections of filaments, where multiple threads converge from different directions, sit the nodes. These are galaxy clusters. Concentrations of matter so extreme, so compacted relative to the surrounding medium, that they represent the densest objects in the universe short of individual black holes. A large galaxy cluster can contain thousands of galaxies, all gravitationally bound, all moving within a shared envelope of extraordinarily hot gas. The temperatures inside that envelope, the intracluster medium, reach hundreds of millions of degrees, sometimes beyond. The nodes are where things end up, or rather, where things concentrate over time. Matter flowing along filaments accumulates at these intersections, thickens, collapses further. The most massive nodes are still growing, still pulling. Nodes occupy a small fraction of the universe's volume but contain a disproportionate share of its dense, visible matter. They are small by cosmic standards, a few megaparsecs across, but heavy in a way that warps what happens around them for enormous distances. Between the filaments, perpendicular to them in some sense, stretch the walls, sheets of matter, flatter than filaments, thinner in one dimension than the other two. They form the boundaries between voids, the panels of the structure, the broad flat surfaces that catch galaxies along their extent. Walls are less studied than filaments and less dramatic than nodes. They have a kind of intermediate character, denser than the voids they border, but less concentrated than the filaments that frame them. Their typical thickness runs somewhere between 15 and 30 million light-years. Their span across the sky can extend to 100 megaparsecs or more. They are not nothing. They hold galaxies in flattened distributions, in long loose arrangements that follow the sheet rather than clustering tightly. And then there are the voids. Voids are the spaces that the filaments and walls surround. They are not simply empty regions where structure hasn't formed yet. They are defined absences, regions where the density of matter runs at 10 to 30% of the cosmic average. They expand, they push outward against the filaments and the walls that border them, driven by the same forces that shape everything else, but in the opposite sense. The underdense regions growing faster than average, while the overdense ones slow under their own weight. A typical void runs between 30 and 150 megaparsecs in diameter. That is, between 100 million and nearly 500 million light-years from one edge to the other. They are not empty of galaxies entirely. Isolated ones do exist inside voids, drifting through those enormous interiors with no cluster to belong to. But the interior density is low enough that crossing a void in any direction means travelling through a sustained near absence of structure. Voids constitute roughly 80% of the total volume of the observable universe. 80, the web, with all its filaments and nodes and walls, the entire scaffold of structure that contains every galaxy cluster, every galaxy, every star that has ever burned, accounts for approximately 20% of the volume. The rest is void. The universe is, by volume, mostly absence. This is the framework. Filaments connecting nodes, walls separating voids, nodes concentrating at intersections, voids expanding between everything else. The structure formed over billions of years, seeded by tiny fluctuations in the density of the early universe, and amplified by gravity into the pattern that fills the sky, invisible to the naked eye, mapped piece by piece with instruments that took most of a century to build. The gas that lives inside this structure, particularly inside the filaments, the gas that fills those enormous elongated threads between galaxy clusters, is the subject of what follows. It has properties that don't quite fit the intuition this architecture suggests. The filaments look, when rendered, like delicate things. Thin threads, subtle, the gas inside them is anything but. The universe should be accountable, that is, in a rough sense. The premise that modern cosmology rests on, the physics of the very early universe, the first few minutes of it, when temperatures were high enough for nuclear reactions to proceed between free protons and neutrons, left a specific signature in the matter that came out the other side. Specific ratios of hydrogen and helium and lithium, ratios that depend on the density of ordinary matter, baryonic matter, at that moment. And those ratios are measurable, because that matter is still here, distributed across the universe, incorporated into stars and gas clouds, and eventually into everything. So you can work backward. You can look at those ratios, the helium fraction in old stars, the abundance of deuterium in ancient gas, and calculate how much ordinary matter the universe made. It's not a guess. The calculation is tight. The number it produces is specific. Baryons, ordinary matter, should constitute about 5% of the total energy content of the universe. Not 5% of visible matter. 5% of everything, including dark matter and dark energy, which sounds small. It is small. But the universe is large enough that 5% of it is an enormous amount of material. That number was established with confidence. And then astronomers went looking for it. They looked in galaxies, stars, gas, dust, the warm halos of ionized hydrogen that wrap around galactic disks. They looked in galaxy clusters, the hot intra-cluster medium that fills the space between galaxies within a cluster, glowing in X-rays, detectable. They looked in the diffuse clouds of gas visible at high redshift, the Lyman alpha forest, the absorption lines left by neutral hydrogen in the spectra of distant quasars. They looked carefully and systematically across decades of observational work, and the tally came up short. Not slightly short, not within a margin of error that you could attribute to instrumental noise or modelling assumptions and a move on. Short by 30 to 40%. Almost half of all the ordinary matter the early universe produced was simply not showing up in any census of the local universe. Galaxies and clusters and diffuse gas, added together, accounted for somewhere between 60 and 70% of the predicted baryonic mass. The rest was missing. This became known as the missing baryon problem, which is, if you think about it, a strange name for it. The baryons weren't missing in the sense of being gone. They couldn't be gone. Matter doesn't disappear. It was missing in the sense that the observational tools available couldn't find it, which meant either the tools were inadequate or the matter was hiding in a form those tools couldn't easily see, or both. It was both. The first serious attempts to locate the missing fraction went looking in the obvious places. Massive black holes, perhaps. Dim, failed stars, objects that never quite ignited, drifting through the galaxy in enormous numbers without being counted. Cold gas clouds too diffuse to detect. Some combination of these, the thinking went, might account for the shortfall. None of it added up, the numbers didn't close, and you could fiddle with the models, push the assumptions in whatever direction was generous, and still come up short. The missing baryons weren't hiding in the obvious places. Then the simulations started getting good enough to say something useful. In the late 1990s, hydrodynamical simulations of cosmic structure formation, models that tracked not just dark matter but ordinary gas as it moved through the expanding universe under gravity, began producing a consistent result. When these simulations ran forward from the early universe to the present day, the gas didn't stay in galaxies. A large fraction of it got pushed out, expelled by supernova winds, by the energy released by forming stars, by the jets of active galactic nuclei. It flowed outward. And as it flowed, as it fell along the gravitational gradients carved by dark matter, it accumulated in the filaments of the cosmic web. The simulations were saying with some confidence that the missing baryons were in the intergalactic medium, not scattered randomly, concentrated in the strands of the cosmic web, in those elongated threads connecting galaxy clusters across hundreds of millions of light years. And they were saying something else, something that took a moment to accept. The gas in those filaments was hot. Hot is doing some work in that sentence, and it's worth being precise about what it means here. Not warm in the way that gas near a galaxy might be warm, photoionized by ultraviolet radiation from young stars, sitting at the temperatures of 10,000 Kelvin or so. The simulations were predicting filament gas at temperatures between 100,000 and 10 million Kelvin, sometimes higher in the densest regions. The reason for this, the mechanism that produces those temperatures, was beginning to become clear. But even before the mechanism was fully worked out, the prediction was already creating a detection problem, a painful one. Gas at 10,000 Kelvin, photoionized and relatively cool, shows up in absorption. Neutral hydrogen leaves marks in quasar spectra, detectable with ultraviolet instruments. That's how the Lyman alpha forest works, and it's a well-developed technique. Gas at 100 million Kelvin, fully virialized inside a galaxy cluster, glows in X-rays, bright enough for X-ray telescopes to image directly. But gas at 100,000 to 10 million Kelvin, the temperature range the simulations were predicting for the filaments, sits between those two windows. Too hot for neutral hydrogen to survive in significant quantities, so UV absorption techniques come up nearly empty. Too cool and too diffused to produce strong X-ray emission, so X-ray telescopes can barely see it against the background. The gas was, in a very specific and almost irritating sense, hiding in the gap between the tools built to find it. This is where the missing baryon problem sat for years. The simulations were pointing at the filaments. The physics was producing a temperature range that made sense mechanically, but the observations kept returning weak signals, marginal detections, results that almost made it above the threshold of significance and then didn't quite. The hypothesis, by the time it had accumulated enough simulation support to feel robust, went something like this. As the universe aged and structure formed, gas that had once been spread relatively uniformly through the intergalactic medium began to flow. Gravity pulled it toward the overdense regions, the seeds of what would become filaments and clusters. As it flowed inward, it accelerated. As it accelerated, it reached speeds that exceeded the local speed of sound in the medium. And when supersonic gas meets the denser material already sitting in a filament, something happens that is violent in a purely physical sense. A shock forms, shock heating is efficient. The kinetic energy of infall converts to thermal energy at the shock boundary with no gentle intermediate step. The gas, cold before the shock, can emerge on the other side at temperatures orders of magnitude higher than what it carried in. That, the simulation said, is what happened to the missing baryons. They fell, they shocked, they heated, they became a diffuse, hot, nearly invisible plasma threaded through the largest structures in the universe, sitting in the cosmic web's filaments, glowing faintly in a frequency range that barely any instrument had been designed to see. The missing matter wasn't gone, it was just harder to look at than anyone had anticipated. Whether the hypothesis was right was, for a long time, genuinely uncertain. The simulations agreed with each other. The physics was coherent, but coherent predictions about invisible things are not the same as confirmed observations of them. Confirmation, it turned out, would take a different kind of tool entirely, and it would arrive from an unexpected direction. Drop something, not metaphorically, pick up whatever is close, something small, and drop it. It falls. Of course it falls, and when it hits whatever surface stops it, there's a sound, a small impact, maybe a bounce. Energy released. The thing that was held up is now down, and something happened in between those two states. Something that produced heat in the collision surface, sound in the air, a brief vibration in your hand if you are still close enough to feel it. That sequence, potential energy becoming kinetic energy, becoming heat at the moment of collision, is the entire engine behind what heats the intergalactic medium. Not metaphorically, not approximately, the same process, just operating at a scale and a speed that makes the dropped object version feel like a rough sketch of the real thing. In the early universe, matter was distributed almost uniformly. Almost. There were variations, tiny fluctuations in density, regions that were fractionally denser than their surroundings, and regions that were fractionally emptier. The differences were small enough that they barely registered. But gravity is patient, and gravity doesn't care about the size of a difference. It only cares that there is one. Denser regions pulled. Not with intention, not with force in the dramatic sense, just with the quiet, persistent tug that any concentration of mass exerts on the matter around it. And matter responded. Gas that sat in the slightly underdense regions around those overdense seeds began to drift. Slowly at first, then less slowly. The drift became motion, the motion became flow, and the flow, given enough time and enough distance to build speed, became something considerably faster than a drift. This is gravitational collapse. The term sounds catastrophic, and sometimes it is, inside a dying star, inside the final moments of something massive. But on the scales of the cosmic web, it is slower, more patient, a process that unfolds over hundreds of millions of years, gas threading down the gravitational gradients carved by dark matter, following the large-scale structure the way water follows terrain, not instantly but inevitably. The gas picks up speed as it falls. This is the part that matters physically, and it's worth sitting with for a moment. An object falling in a gravitational field converts potential energy into kinetic energy at a rate set by the depth of the gravitational well it's falling into. The deeper the well, the faster the object moves by the time it reaches the bottom. Galaxy clusters are very deep wells. The dark matter halos that anchor them are massive enough that gas falling from the filament into the cluster can reach speeds of hundreds of kilometers per second, sometimes faster, hundreds of kilometers per second. The gas isn't moving that fast when it starts. It starts cold, diffuse, barely moving relative to the structures around it. But the fall is long, the distances involved are enormous, and by the time the gas has traversed a significant fraction of a filament, falling toward the overdense region at its end, it has accumulated speed in the way that anything accumulates speed, when something pulls on it for long enough without anything pushing back. This is where the temperature comes from, not from an external heating, not from radiation pumped in from a nearby source, from the conversion of that accumulated kinetic energy into something else entirely. The something else is heat, but the conversion requires a mechanism, and the mechanism is not immediate. It doesn't happen simply because the gas is moving fast. A single fast-moving particle is not hot. Heat is a collective property, a measure of the random thermal motion of many particles, not the organized motion of all of them moving in the same direction at the same speed. Falling gas is organized, all of it moving in roughly the same direction toward the overdense region at the bottom of the gravitational well. Organized motion, however fast, is kinetic energy, not heat. The conversion from one to the other requires something to disrupt the organization, something to randomize the motion, to take the coordinated infall and scatter it in every direction simultaneously. That something is a shock. When infalling gas reaches a region where it can no longer flow freely, where it runs into denser, slower moving material that has already accumulated, the collision is not gentle. The incoming gas is moving supersonically, faster than the pressure waves that would normally signal to the surrounding medium that something is coming. The medium has no warning. There is no gradual compression, no smooth transition. Instead, there is a boundary, a shock front, where conditions change abruptly over a distance that is, in some cases, barely larger than the mean free path of the particles involved. At that boundary, something happens to the organised infall that can only be described as a kind of mechanical catastrophe. The kinetic energy of the infalling gas, all that accumulated speed built up over hundreds of millions of years of gravitational freefall, gets converted into thermal energy at the shock. The organised motion becomes random motion. The particles that were all moving together in the same direction at the same speed scatter. The energy doesn't disappear. Energy doesn't disappear, it redistributes. And what a redistribution of kinetic energy into random particle motion looks like, measured as a physical property of a gas, is temperature. High temperature, sometimes very high temperature. The efficiency of this conversion depends on the strength of the shock, on how fast the infalling gas was moving relative to the sound speed of the medium it's hitting. The ratio of those two speeds is the Mach number. A Mach number of 1 means the gas is moving exactly at the speed of sound. A Mach number of 10 means it's moving 10 times faster. At the outer boundaries of large-scale cosmic filaments, where pristine, cold, never-before-shocked gas is falling in from the surrounding voids for the first time, Mach numbers can reach into the hundreds, sometimes higher. The higher the Mach number, the more efficient the shock. The more efficient the shock, the hotter the gas that comes out the other side. Gravity did not set out to heat the intergalactic medium. Gravity doesn't set out to do anything. It pulls, matter responds, matter accelerates, matter collides, and the collision produces heat as an almost incidental consequence of the energy that was stored in the separation between things. The heat is what potential energy becomes when it has nowhere left to go. This is why the space between galaxies is not cold. Not because something is burning out there, not because any star or any galaxy is warming it from a distance, but because the structure of the universe itself, the large-scale arrangement of matter and void, creates gravitational gradients that gas has been falling down for billions of years. And falling, given enough distance and enough time and the right kind of collision waiting at the bottom, is indistinguishable from heating. Gravity is not usually thought of as a thermal process. It is thought of as a structural one, the force that holds things together, that shapes orbits, that curves the paths of light. But at the scale of the cosmic web, what gravity produces in the end is warmth. A specific, measurable, physically real warmth distributed through the longest structures the universe contains. The next question is, what happens at the exact moment of collision? What a shock front actually is, and what crossing one costs. Sound needs time, not much time, not time you'd notice in a conversation or across a room, but time. The speed of sound in air at room temperature is about 343 meters per second, which feels fast until you're watching a storm and counting the gap between the lightning and the thunder. Light arrives instantly. Sound takes a moment. The gap is the distance divided by that speed, and it's real, measurable, a physical property of the medium the sound is moving through. What sound actually is, though, is pressure. A disturbance that propagates by compressing the medium ahead of it, passing the compression forward from particle to particle in a chain. Each particle pushes the next pushes the one after. The disturbance travels. This is how information about a disturbance moves through a gas. This is how the gas knows something is coming. The speed of that propagation is not arbitrary. It depends on the temperature and density of the medium. Cold, diffuse gas has a lower sound speed than hot, dense gas. In the intergalactic medium, in gas that hasn't yet been heated by any shock, the sound speed is low, very low. The gas is cold, spread thin, barely interacting with itself. A pressure disturbance travels through it slowly. An infalling gas moves fast. Here is what happens when something moves through a medium faster than the speed of sound in that medium. The medium doesn't know it's coming. That's the core of it. Normally, when an object moves through a gas at subsonic speeds, pressure waves run ahead of it, compressing the gas slightly, giving it time to adjust, to part, to flow around the object in an orderly way. The gas has warning. It reorganizes before the object arrives. The transition is smooth. Supersonic motion removes the out warning entirely. The object, or in this case the infalling gas, is moving faster than the pressure waves that would announce it. Nothing runs ahead. The medium has no signal, no preparation time, no gradual compression to ease the transition. And then the gas arrives. What forms at the leading edge is a shock front, a boundary, a surface across which conditions change not gradually but essentially instantly over a distance that, in some shocks, measures in particle mean free paths rather than megaparsecs. The thickness of a shock front is, physically, the smallest meaningful length scale in the system. It is thin in the way that the edge of something real is thin. On one side of that boundary, cold, fast-moving, organised gas, all of it flowing in the same direction. Kinetic energy, not heat. On the other side, something very different. The conversion that happens at the shock front is not a process in the usual sense. It doesn't unfold over time, doesn't proceed through intermediate steps you could watch. It is a boundary condition. You cross it and you are changed. The gas that passes through a strong shock front goes from organised motion to randomised motion in a transition that is, from the gas's perspective, essentially discontinuous. Before the shock, particles moving together coordinated a flow. After, the same particles, the same total energy, but the energy redistributed. The organised kinetic energy of infall becomes the random thermal motion of a hot gas. The particles are still moving at similar speeds, roughly, but now they're moving in every direction, scattered, colliding with each other, thermalizing. What was a wind becomes a temperature. The efficiency of this conversion is what makes shocks such powerful heaters. In many other heating processes, energy is transferred gradually, leaks out through radiation, gets shared unevenly through the system. A shock doesn't allow for gradual. The boundary is crossed, the energy converts. The gas comes out the other side hot, and how hot depends almost entirely on how fast it was moving when it hit. The relationship between infall speed and post-shock temperature is specific. For a strong shock, the kind produced by gas falling supersonically into a dense filament or cluster, the post-shock temperature scales with the square of the infall velocity. Double the infall speed, and the temperature on the other side of the shock increases by a factor of 4. Triple it, factor of 9. The dependence is quadratic, which means small increases in speed produce large increases in temperature. Gas falling into a massive galaxy cluster from the surrounding filament can reach infall velocities of several hundred kilometers per second. At those speeds, the post-shock temperature reaches tens of millions of Kelvin. The shock is doing what no external heater could do as efficiently, converting the entire kinetic energy budget of the infall into thermal energy in a single boundary crossing. The Mach number of the shock, the ratio of infall speed to the local sound speed, sets the strength of this conversion. In the intergalactic medium, where the pre-shock gas is cold and the sound speed is low, accretion shocks at the outer edges of filaments and clusters can reach Mach numbers of 10, 100, occasionally higher. Strong shocks, very efficient ones. The gas that comes through them is not gently warmed. It is, in the most literal physical sense, thermalized violently. The word violent feels almost too casual for it, but I'm not sure what word fits better. The organised energy of a billion years of gravitational freefall converted into random heat in a boundary thinner than anything you could draw. This is why the intergalactic medium is hot. Not because something is burning out there, not because the universe retained heat from its earliest moments, but because gas has been falling for billions of years, building speed, and then hitting these boundaries, over and over, in every filament, at every cluster edge, shock after shock, each one converting infall into temperature, each one adding to the thermal budget of the medium that fills the cosmic web. The outer boundaries of large-scale structure, the places where cold void gas meets the heated filament for the first time, are where the strongest shocks occur. The most pristine gas, never previously shocked, hitting the filament edge at the highest relative velocities. What comes through those boundary crossings is the WHIM, the warm-hot intergalactic medium, a name for what the gas becomes after the shock has done its work. After the organised fall is over and only the heat remains, that heat has a range, a specific measurable range that the next chapter will try to hold clearly. Because understanding what the WHIM actually is, its temperature, its density, its physical state, is what makes everything that follows legible. Try to imagine a substance with no smell, no colour, no texture you could feel even with the most sensitive instrument you own. Something that, if you passed through it, would leave no trace on your skin, no sensation in your lungs, no sound in the air around you. Something that occupies space, measurably, physically, with real mass and real temperature, but registers on none of the senses that evolved to tell you what the world is made of. This is not a thought experiment about nothing. It is a description of something specific, a substance with a name, a temperature range, a density, a physical state, a distribution across the largest structures in the universe. It is called the warm-hot intergalactic medium, the WHIM. And despite its near total invisibility to every instrument we built before we knew to look for it, it is, by most current estimates, the single largest reservoir of ordinary matter in the observable universe today. Not dark matter, not dark energy, ordinary matter. The stuff that makes atoms, the stuff that makes you. Start with the temperature, because the temperature is the most immediately surprising property and everything else follows from it. The WHIM occupies a temperature range between roughly 100,000 Kelvin and 10 million Kelvin. That range is not uniform across all filaments and all locations. The cooler end near 100,000 Kelvin is found in the outer regions of filaments, in gas that has passed through weaker shocks, in material that was moving more slowly when it hit the boundary, and came through with less thermal energy. The hotter end, approaching 10 million Kelvin and occasionally beyond, is found in denser regions, closer to galaxy clusters, in gas that fell faster and shocked harder. The Sun's surface sits at about 5,700 Kelvin. The solar corona, the Sun's outer atmosphere, which is itself considered puzzlingly hot, reaches somewhere between 1 and 2 million Kelvin. The WHIM, at its upper end, is however 10 times hotter than the solar corona. These numbers sit there on the page looking like they should feel more dramatic than they do. I keep expecting them to land harder. Maybe they do, and I've just looked at them too many times, but the physical consequence of those temperatures is not abstract. At 100,000 Kelvin, hydrogen cannot hold on to its electron. The thermal energy of the surrounding medium is too high. The electron gets knocked loose, and what remains is a bare proton, a hydrogen nucleus with nothing around it. At 1 million Kelvin, helium is fully stripped. At 10 million Kelvin, even heavier elements, oxygen, carbon, nitrogen and me, are in extremely high ionization states, missing most or all of their electrons. The WHIM is not a gas in the conventional sense. It is a plasma, not because of some exotic condition, but for the straightforward reason that its temperature is high enough that neutral atoms cannot survive in it. The electrons and nuclei that make up its matter are separated, moving freely, interacting electromagnetically, rather than through the neutral atom chemistry of colder environments. The density is where the WHIM becomes genuinely hard to picture, not because the number is complicated, but because it describes something so sparse that comparison struggles to reach it. Fewer than 100 hydrogen ions per cubic meter. That is the particle density of the WHIM, sometimes far fewer, depending on location. The outer regions of filaments, away from the dense core, can drop to densities of 1 or 2 particles per cubic meter. A cubic meter of air at sea level contains roughly 10, followed by 25 zeros of molecules. A cubic meter of the best laboratory vacuum ever sustained on Earth still holds something like 10 million particles. The WHIM holds fewer than 100. It is not the emptiest thing in the universe. The cosmic voids that the filaments border have densities sometimes 100 times lower still. But by any standard built from human experience or human-scale materials, the WHIM is extraordinarily sparse. You could drift through a cubic kilometre of it, and the probability of a single particle collision would be negligible. And yet it has mass. Real, accumulated, significant mass. because the filaments that contain it are enormous. A single cosmic filament, 500 to 800 million light-years long, 2 to 5 megaparsecs across, multiplies that sparse density over a volume so huge that the total mass it contains becomes meaningful. The WHIM is estimated to hold somewhere between 40 and 50% of all baryonic matter in the universe at the present epoch. Thin everywhere, enormous in total. The distribution of the WHM follows the distribution of the cosmic web's filaments. It is not spread uniformly through intergalactic space. The voids, those vast underdense regions that make up roughly 80% of the universe's volume, are emptier still. The WHIM concentrates in the threads along the spines of filaments, denser toward the core and thinning towards the edges, always threaded through the large-scale gravitational structure that shaped it. This distribution is not coincidental. The WHIM is where it is because the shocks that produced it are where they are. The shocks occur at the boundaries of filaments and clusters, where infalling gas meets the denser accumulated material. The heated gas doesn't travel far from where it was shocked. It thermalizes and settles roughly where the shock found it, filling the filament volume with plasma at temperatures that reflect the depth of the gravitational well that accelerated the gas before impact. The WHIM is, in this sense, a map of where shocks have happened. Its temperature distribution traces the strength of those shocks. Its density distribution traces the density of the filaments that hosted them. It is a record of gravitational energy converted to heat over billions of years, written in plasma across the largest structures the universe contains. One property that follows from the plasma state is worth noting, not because it changes the picture dramatically, but because it closes a loop. In a neutral gas, electromagnetic radiation passes through relatively freely. Neutral hydrogen is transparent to most wavelengths that don't happen to match its specific absorption lines. But a plasma interacts with electromagnetic radiation differently. Free electrons scatter photons. The interaction depends on the density and the energy of both the photon and the electron. In the WHIM, the density is low enough that this scattering is weak. The plasma is, in the technical sense, optically thin. Radiation passes through it. The WHIM doesn't glow the way a dense plasma would. It doesn't emit the kind of bright X-ray signal that hot, dense intracluster gas produces. It emits faintly at low intensity, spread across an enormous volume, and the signal is easily lost in the background noise of other sources. This is one of the reasons it took so long to confirm observationally. The WHIM has all the physical properties you would expect of a major component of the universe: real temperature, real mass, real physical extent. It also has the emission signature of something that does not want to be found. What it took to find it, the specific tools and methods, and something completely unexpected that arrived from an unrelated corner of astrophysics is a different chapter. But it's worth carrying forward what the WHM is before moving to the question of how we know. Half the ordinary matter in the universe, 100,000 to 10 million Kelvin, fewer than 100 particles per cubic meter, a plasma, fully ionized, threaded through the filaments of the cosmic web, faint to the point of near invisibility. That is what the WHIM is. The sun is not easy to look at. Even at 93 million miles, filtered through an atmosphere, behind clouds, reduced to the orange disk of late afternoon, it is the brightest thing in the sky by so much that nothing else competes. It has shaped every biological clock that ever evolved on this planet. The circadian rhythms in your cells right now, the ones that are probably telling you it is time to rest, are responses to a star that is 89 light seconds away. Its influence is not subtle, and the surface of it, the photosphere, the layer from which the light you see actually escapes, sits at 5,773 Kelvin. That is hot in any frame that matters to a human being. At that temperature, iron is not just molten but vaporized. Silicate rock has long since become gas. Every molecule you can name has been stripped apart into individual atoms. The chemistry of everyday material simply doesn't exist at 5,700 Kelvin. It has been replaced by something simpler and more violent. This is the surface of a star. The thing that grows food, the thing that has warmed every ocean this planet has ever had. Now go up, not in space but in temperature. Move outward from the photosphere through the chromosphere, a thin turbulent layer, and into the corona, the sun's outer atmosphere, the faint halo visible during a total solar eclipse as a pale, ghostly ring around the blotted disk. The corona runs at somewhere between 1 and 2 million Kelvin. This is, depending on how you look at it, either a well-known fact or an outright scandal. The surface of the sun is 5,700 Kelvin. The corona is 1,000,000. Moving away from the heat source, temperature rises by a factor of nearly 200. No other phenomenon in everyday thermodynamics does this. Heat flows from hot to cold, not the other way. And yet here is the sun's outer atmosphere, sitting at temperatures that would be considered extreme by almost any astrophysical standard. The reasons for coronal heating are still not fully resolved, which I find oddly comforting. The sun is close, incredibly close. We have sent spacecraft into its outer atmosphere, and the mechanism that heats its corona remains, in meaningful ways, an open question. Some combination of magnetic reconnection events and magnetohydrodynamic waves, the current thinking goes, but the details are contested. At 1,000,000 Kelvin, hydrogen is fully stripped of its electrons, helium is stripped, iron is missing most of its 26. The corona is not a gas in any chemical sense. It is a fully ionized plasma, transparent to most wavelengths, glowing in X-rays that Earth's atmosphere blocks before they can reach the ground. 1 to 2 million Kelvin. The sun's outer atmosphere, a number that already asked you to let go of ordinary reference points. The WHIM runs hotter. At the low end of its temperature range, around 100,000 Kelvin, the WHIM is already 17 times hotter than the solar surface. Hydrogen cannot exist there as a neutral atom. The thermal energy in the medium is too high, the collisions too frequent and too energetic for an electron to stay bound to a proton for any meaningful duration. At the middle of its range, around 1,000,000 Kelvin, the WHIM matches the solar corona. Same temperature, same physical consequences. Fully ionized hydrogen, fully ionized helium, heavier elements in extreme ionization states. Their electron shells progressively stripped by the thermal environment they sit in. But the WHIM doesn't stop there. At its upper end, in the densest, most shocked regions near galaxy clusters, temperatures reach 7 to 10 million Kelvin. The eROSITA all-sky survey, stacking thousands of cosmic filaments, returned a best-fit temperature for the X-ray emitting WHIM of just under 7 million Kelvin. Individual filament measurements push toward 10. 7 million Kelvin is 5 to 10 times hotter than the solar corona, is roughly 1,200 times hotter than the surface of the sun. At that temperature, oxygen, which has 8 electrons to lose, has lost most of them. Carbon, neon, iron in extreme states. The matter in the WHIM at this temperature is not simply hot gas. It is a plasma so energetic that the distinction between different elements, in terms of their chemistry, their bonding behavior, their familiar material properties as stands, has become entirely meaningless. There are only nuclei and free electrons, all moving fast, all colliding, none of them bound to anything. Here is the thing that I keep returning to, the thought that doesn't quite settle no matter how many times I approach it. The sun is burning. Nuclear fusion in its core, hydrogen crushed into helium under pressures that no material structure could survive, releases energy that then spends tens of thousands of years fighting its way outward through the sun's dense interior before finally escaping as light. The surface temperature of the sun is the result of that energy, finally free, finally radiating away from the most powerful, sustained reaction in the solar system. The WHIM has no fusion reactor, no core, no burning at all in the nuclear sense. The gas out there between the galaxies is hot not because something inside it is exploding, but because it fell. Because it was cold and diffuse and gravity pulled it, and it fell for hundreds of millions of years and hit something. The temperature, all 7 to 10 million Kelvin of it, is the echo of that collision. Potential energy, kinetic energy, heat, no fire required. The sun heats its corona through mechanisms we still don't fully understand, through magnetic energy and wave dynamics and processes that remain contested. The WHIM heats itself, if you can call it that, through nothing more exotic than falling, the simplest thing a massive object can do in a gravitational field. The space between galaxies runs hotter than the outer atmosphere of the nearest star, not in a few regions, not as an anomaly, as the normal condition of the intergalactic medium in the filaments of the cosmic web. This does not announce itself. There is no way to feel it from here. The WHIM sits at those temperatures silently, invisibly, in a plasma so diffuse that a spacecraft travelling through it would register nothing on any instrument designed for human environments. The heat is real, the temperature is real, but density so low means that the total thermal energy per unit volume is modest. Hot and sparse is not the same as hot and dense. You would not be burned by it. You would pass through without knowing. The temperature is not about your comfort. It is about what happened to the matter. And what happened to the matter, it turns out, was almost impossible to see. There is a version of the missing baryon problem that feels like a failure of observation. Like astronomers simply weren't looking in the right place or weren't looking hard enough, and the matter was out there all along, waiting to be found by anyone who bothered. That version is not quite right. The WHIM's near invisibility is not an accident of insufficient effort. It is a direct physical consequence of what the WHIM is. Its temperature range, its density, its ionization state all conspire to place it precisely where the instruments built to survey the universe are least sensitive. This is not bad luck. It is physics being consistent with itself. To understand why, you have to understand how astronomers detect gas in the first place, not as an abstract tool, but as a physical process with specific requirements and specific limits. The most successful technique for detecting diffuse gas across cosmological distances is absorption spectroscopy. The idea is straightforward, or at least it sounds straightforward. A bright background source, a quasar, emits light across a broad range of wavelengths. That light travels toward us across billions of light years, passing through whatever gas sits between the quasar and our telescopes. If that intervening gas contains atoms in a particular state, those atoms absorb specific wavelengths from the quasar's light, leaving dark lines in the spectrum we receive. The pattern of those lines tells us what the gas is made of, how fast it's moving, roughly how much of it there is. This technique works beautifully for gas at around 10,000 Kelvin. At that temperature, hydrogen exists partly as neutral atoms, the familiar HI of spectroscopic notation, with its electron still attached, still capable of absorbing photons at the specific wavelengths that hydrogen absorption requires. The Lyman alpha forest, the dense thicket of absorption lines in the spectra of distant quasars, is a map of neutral hydrogen across cosmic time. It works. It has produced some of the most detailed maps of the intergalactic medium at high redshift. The WHIM is not at 10,000 Kelvin. At 100,000 Kelvin, neutral hydrogen does not survive in any significant quantity. The thermal energy of the medium is high enough to ionize it, to knock the electron free and leave a bare proton. You cannot detect what isn't there. The Lyman alpha technique, the workhorse of intergalactic gas detection, goes essentially blind at the temperatures where the WHIM lives. So you go to higher energy tracers. Oxygen is more useful here. At temperatures approaching 100,000 Kelvin, oxygen exists in the O6 state, meaning it has lost 5 of its 8 electrons. O6 has its own absorption lines in the far ultraviolet, and these have been used to trace the cooler end of the WHIM with some success. Instruments like the Cosmic Origin Spectrograph aboard the Hubble Space Telescope, and earlier the Far Ultraviolet Spectroscopic Explorer, have detected O6 absorbers along many quasar sightlines, giving glimpses of gas at the lower temperature boundary of the WHIM range. But O6 traces only the coolest WHIM, the gas sitting around 100,000 to 1,000,000 Kelvin, the bottom of the range. For hotter gas, Oxygen moves to higher ionization states, O7 and O8, which absorb at X-ray wavelengths, not ultraviolet. Detecting those lines requires X-ray spectroscopy. An X-ray spectroscopy of faint diffuse intergalactic gas is, to put it plainly, very hard. The difficulty is not conceptual, it is instrumental. X-ray telescopes like Chandra and XMM Newton carry gratings that disperse X-ray light into spectra. The effective area of those gratings at the wavelengths where O7 and O8 absorb is small. Small effective area means few photons collected per unit time, which means long observations needed for any detection above noise. And the WHIM, spread thin across millions of light-years of filament, produces absorption features of weak equivalent width, marginal, at the edge of what the instruments can resolve. Several claimed detections of O7 absorption in quasar sightlines have been published over the years, including the Nicastro 2018 observation of two absorbers in the spectrum of Blazar, 1ES1553 plus 113. Most remain technically marginal, debated, not yet confirmed at the kind of significance level that settles questions definitively. The emission side is no easier. Hot, dense gas emits X-rays. This is how galaxy clusters are mapped. The intracluster medium, sitting at 100 million Kelvin and compressed to relatively high densities within the cluster's gravitational potential, glows in X-rays brightly enough for current telescopes to image directly. The emission is strong because X-ray emissivity scales roughly with the square of the density. Dense gas emits far more per unit volume than diffuse gas. The WHIM is not dense, fewer than 100 particles per cubic meter. The emissivity of gas that's sparse, even at 10 million Kelvin, is low, very low. The signal per unit volume is weak, and the WHIM is spread across volumes so enormous, filaments hundreds of millions of light-years long, that the surface brightness on the sky, the signal per square degree, is correspondingly faint. The X-ray background is not empty. It contains contributions from unresolved point sources, from hot gas in galaxies and clusters at various distances, from the cosmic X-ray background itself. The WHIM's emission signal sits below or barely above these backgrounds. You cannot simply point a telescope at a filament and see it glow, the way you can point at a galaxy cluster and immediately recognize its X-ray halo. Between the UV absorption window and the X-ray emission window there is a gap, a temperature range that neither technique accesses cleanly, and the WHM, most of it, sits inside that gap, too hot for neutral hydrogen to trace, too cool for strong X-ray emission, too diffuse for surface brightness detection against a noisy background. The gas contains roughly half the ordinary matter in the observable universe, and for decades it registered on almost no instrument built to survey the cosmos. This is not quite the same as being invisible. Nothing is truly invisible in physics. Something that has temperature emits radiation. Something that has charged particles interacts with passing electromagnetic fields. There was always a signal. The question was whether any instrument was sensitive enough to pull it above the noise. Sensitivity, it turned out, was not the only path. The signal the WHM couldn't produce, clearly in emission or absorption, it left in something else entirely. A different kind of trace. One that nobody had initially designed to look for the missing baryons at all. The tool that finally helped close the census was not a telescope pointed at a filament. It was a flash, a millisecond pulse of radio energy from a source billions of light-years away, passing through every intervening electron on its way to Earth, including, it turned out, the electrons in the WHIM. Light does not know it is carrying information. A photon leaving a quasar, one of those extraordinarily luminous objects powered by matter falling into supermassive black holes at the centers of distant galaxies, departs with a specific energy, a specific wavelength, part of a broad continuum of emission that the quasar produces more or less continuously. The photon travels. It crosses intergalactic space at the only speed it knows. It passes through whatever sits between the quasar and wherever it ends up, which might be a detector on a satellite orbiting a small planet in an unremarkable galaxy, billions of years after the photon was emitted. Along the way, things happen to it, or rather, things almost happen to it most of the time. Intergalactic space is sparse enough that the vast majority of photons pass through without interacting with anything. But occasionally, a photon with exactly the right energy, matching exactly the energy gap between two quantum states of an atom or ion it encounters, gets absorbed. The atom takes the photon's energy, the photon ceases to exist in that form, and the atom, briefly excited, releases the energy in a different direction, effectively removing that specific wavelength from the beam, travelling toward the detector. By the time the light arrives, billions of years and billions of light years later, the spectrum is no longer a smooth continuum. It has gaps in it, dark lines at specific wavelengths, each one a record of an encounter with specific matter somewhere along the path. The spectrum, if you know how to read it, is a receipt. Every absorption line a timestamp, a location, a signature. Not written intentionally, just accumulated, the way any surface accumulates what lands on it. Reading that receipt requires knowing what each line means. The wavelength of an absorption feature identifies the ion that produced it, because each element in each ionization state has a specific set of energy transitions with specific wavelengths. Hydrogen absorbs at the Lyman alpha wavelength, 121.6 nanometers in the far ultraviolet. Carbon in various ionization states absorbs at its own characteristic wavelengths. Oxygen, which is particularly useful for tracing the WHIM, absorbs at wavelengths that shift depending on how many electrons it has managed to keep. O6, oxygen that has lost 5 of its 8 electrons, absorbs at around 103 nanometers, also in the far ultraviolet. It exists at temperatures around 100,000 to 1,000,000 Kelvin, the cooler end of the WHIM range. Detecting O6 absorbers in quasar spectra requires ultraviolet-capable space telescopes, because Earth's atmosphere blocks far ultraviolet light before it reaches the ground. The Hubble Space Telescope's Cosmic Origin spectrograph, and before it the Far Ultraviolet Spectroscopic Explorer, have catalogued hundreds of O6 absorption systems along sightlines to bright quasars, building a statistical picture of warm intergalactic gas across a range of redshifts. That statistical picture confirmed that warm gas exists in the filamentary structure of the cosmic web. But O6 traces only the cooler fraction of the WHIM. The hotter gas, sitting at several million Kelvin, has pushed oxygen to higher ionization states. O7, oxygen missing 6 electrons, and O8 missing 7, absorb not in the ultraviolet but at X-ray wavelengths, around 21.6 and 18.97 angstroms respectively. Detecting those lines requires X-ray spectroscopy of sufficient resolution and sensitivity to isolate weak absorption features against the bright continuum of a background quasar. This is where the difficulty becomes acute. X-ray absorption spectroscopy of diffuse intergalactic gas is constrained by the instruments available to do it. Chandra and XMM, Newton, the two most capable X-ray observatories currently operating, carry grating spectrometers that can, in principle, resolve the O7 and O8 absorption lines if they are present in a bright enough background source. The constraint is effective area. At the wavelengths where these lines appear, the gratings collect relatively few photons even from bright sources, which means the signal-to-noise ratio in any individual observation is low. Detecting a weak absorption line against a noisy continuum requires either an extremely bright background source and extraordinarily long observation time, or both. The number of quasars and blazars bright enough in X-rays to make this feasible is small. The observations required are expensive in telescope time. The expected signal based on models of the WHIM column density along any given sightline is weak, an equivalent width of a fraction of an electron volt sitting in a spectrum with substantial noise at that wavelength. Marginal detections are not a failure of effort. They are the predictable result of asking a difficult physical question with instruments built for other purposes. The Nicastro 2018 observation sits in this context. Fabio Nicastro and colleagues used XMM Newton's reflection grating spectrometer to examine the X-ray spectrum of the blazar 1ES1553+113 in a long dedicated observation designed to search for WHIM absorption. The blazar was chosen because it is one of the brightest X-ray point sources in the sky, maximizing the number of photons available for spectral analysis. The sight line to 1ES1553+113 was chosen partly because prior ultraviolet observations had identified O6 absorbers along the line of sight, providing redshift priors at which to look for the corresponding X-ray signature. What the analysis returned were two features in the spectrum: absorption-like signals at wavelengths consistent with O7 at redshifts of approximately 0.4339 and 0.3557. At those redshifts, the authors identified small numbers of galaxies within projected distances of less than 1.5 megaparsecs, suggesting the presence of filamentary structure that could host the WHIM gas at the required column density. The detection was reported at a significance of around 3.5 sigma for the combined signal, which sits at the boundary that astrophysics conventionally treats as suggestive but not definitive. 5 sigma is the threshold for a confident detection. 3 to 4 sigma is the territory of probable detections that have a meaningful probability of being statistical fluctuations. Subsequent analyses of the same data by independent groups produced somewhat lower significance estimates, and the features remain technically contested in the literature. This is not a failure of the observation. It is an honest account of what the available instruments can do with the available sources. The XMM Newton gratings were not designed with WHIM detection as their primary purpose. They were being pushed to the edge of their sensitivity. The fact that something was found, even at marginal significance, was itself informative about where to look and what to look for. The absorption line method, despite its difficulty at X-ray wavelengths, remains the most physically direct way to study the WHIM. When a clear O7 or O8 absorption feature is detected along a well-characterized sight line, it tells you something specific, that there is hot, highly ionized gas at that redshift at that location, with a column density high enough to produce the observed equivalent width. It is localized information, a sightline measurement, narrow and specific, telling you what sits along one particular line through intergalactic space. The limitation is coverage. One sightline tells you about one sightline. Building a statistical picture of the WHIM from absorption measurements requires many sightlines, many bright background sources, many long observations. Progress has been steady but slow, constrained always by the brightness of the available background sources and the sensitivity of the available spectrometers. What the method produced, even in its marginal form, was evidence, not proof. Evidence that hot gas with O7 column densities consistent with WHIM models does exist along at least some sightlines through intergalactic space. Combined with the simulation predictions and the O6 detections at lower temperatures, the picture was becoming coherent if not yet confirmed. A different kind of observation, not an absorption measurement, not a pointed stare along a single sightline, would eventually produce the first statistical confirmation with enough significance to shift the conversation. It arrived not from a telescope pointed at a quasar, but from something that happened to pass through the WHIM on its way to us without any prior arrangement, leaving its own kind of trace in the signal. It lasts a millisecond, sometimes less. A burst of radio waves, intense enough to outshine an entire galaxy for the duration of its flash, arriving from somewhere billions of light years away, lasting roughly as long as a blink, and then gone. Fast radio bursts were first identified in archival data in 2007, spotted in observations originally made for a different purpose entirely, a survey of pulsars in the Magellanic Clouds. The burst was there in the data, bright and brief, and it didn't match anything the observers were looking for. It came from outside the galaxy. Its dispersion was too large for any source within the Milky Way. Something out there at cosmological distance had produced an extraordinarily energetic pulse of radio emission and sent it across billions of light years of space. What causes them is still being worked out. The leading candidate is magnetars, neutron stars with magnetic fields strong enough to produce catastrophic flaring events, the kind of event that would release in a millisecond more energy than the sun emits over days. Other mechanisms are possible. The origin is not fully settled, and the details of what produces the flash are, for the purposes of what follows, less important than what the flash does on its way to us. What it does is accumulate delay. Radio waves travelling through a plasma don't all travel at exactly the same speed. Lower frequency waves travel slightly slower than higher frequency waves when passing through ionized gas. The difference is small, a fraction of a percent, but it is real and it accumulates over distance. A pulse that starts out as a simultaneous burst across a range of radio frequencies arrives at a detector, spread out in time, the lower frequencies trailing behind the higher ones, by an amount that depends on how much ionized gas the pulse passed through. This effect is called dispersion, and the amount of it, the dispersion measure, is a direct integral of the electron column density along the entire path from source to detector. Every free electron between the source and us leaves a measurable contribution to the dispersion measure. The electrons in the Milky Way's interstellar medium contribute. Electrons in the host galaxy of the FRB contribute, and electrons in the intergalactic medium, the diffuse ionized gas spread across billions of light-years of cosmic filaments and voids, contribute proportionally to how much of the path they occupy. The dispersion measure is, in this sense, a physical measurement of the total ionized content of the universe along a specific line of sight. Not a proxy, not an indirect inference. Direct integral of electron density with distance, encoded in the arrival timing of radio waves across a frequency band. When you localize an FRB to its host galaxy, when you can determine its redshift and therefore its distance, you can subtract the known contributions from the Milky Way and estimate the host galaxy's contribution. And what remains is the intergalactic component, the electrons in the space between galaxies, the electrons in the cosmic web. The relationship between intergalactic dispersion measure and redshift was formalized by the Jean-Pierre Macquart and colleagues in 2020, using a sample of localized FRBs to establish what became known as the Macquart relation. The basic prediction, derived from the standard cosmological model, is that the average intergalactic dispersion measure should increase linearly with redshift, because more redshift means more distance, and more distance means more intervening plasma to disperse the signal. The data confirmed this. The localized FRBs, each one traced back to a specific galaxy at a known distance, produced dispersion measures that tracked the predicted relationship. The intergalactic medium was there. Its electron content was consistent with the baryon density predicted by Big Bang nucleosynthesis. The matter that had seemed missing from the census was producing a measurable signal in the timing of radio pulses from across the universe. This is the part worth pausing on, because it resolves something that had been genuinely unresolved for decades. The missing baryon problem was not a small discrepancy. 30 to 40% of the predicted ordinary matter in the universe was unaccounted for by conventional observation. That is not a rounding error. That is a large fraction of everything. The FRB dispersion measurements didn't just hint that the matter was in the intergalactic medium, they quantified it. They produced a measurement of the total electron content along many independent sightlines through the cosmos, and that content, when converted to a baryon density using standard assumptions about the ionization state of intergalactic gas, matched what the early universe was supposed to have made. The Harvard-Smithsonian Center for Astrophysics framing of this result is useful for its directness. Researchers there, part of the team analysing a large sample of localised FRBs from the DSA 110 interferometer at the Owens Valley Radio Observatory in California, described the finding in terms that cut through the usual hedging of scientific language. The missing boson problem, as they characterized it, was never about whether the matter existed, it was always about where it was. Now, with FRBs providing sightline after sightline through the intergalactic medium, the answer has a quantitative foundation. 3/4 of the missing baryons, they reported, are floating between galaxies in the cosmic web. 3/4, not a statistical hint, not a marginal excess above background, a measured fraction derived from the dispersion of real signals from real sources at known distances, consistent across multiple independent samples and consistent with the predictions of cosmological simulations that have been pointing at the filaments for 30 years. The FRB method confirmed what the simulation suspected and what the marginal X-ray detections and ultraviolet observations had been suggesting. The matter was always in the intergalactic medium, in the filaments, in the warm-hot plasma threading the cosmic web. There is something slightly strange about this, and I find it worth naming. The tool that resolved one of cosmology's most persistent accounting problems was not designed for the purpose. No one built a fast radio burst detector to look for missing baryons. FRBs were found in data collected for other reasons. Their dispersion properties were studied because dispersion is a fundamental observable property of any radio pulse travelling through a plasma. The Mach relation emerged from applying standard physics to a new class of object. The baryon confirmation was, in a real sense, a consequence of the universe cooperating, of the dispersion effect being exactly the right physical process to encode intergalactic electron content in a detectable way. The measurement works because the intergalactic medium is ionized, because the WHIM, with its temperatures high enough to strip hydrogen of its electrons, contributes free electrons to the path of every FRB that passes through it. The same thermal state that made the WHIM nearly invisible to conventional observation, too hot for neutral hydrogen detection, too diffuse for strong X-ray emission, makes it transparent to radio waves in a way that imprints its presence on the timing of those waves. The invisibility and the detectability are consequences of the same property. The high temperature that hid the WHIM from ultraviolet and X-ray instruments is the same high temperature that ionized its gas and made it legible to the dispersion of radio pulses. A millisecond flash from a magnetar billions of light years away, spreading across radio frequencies as it travels, accumulating the signature of every electron it passes through, arriving at a radio telescope as a slightly smeared pulse, whose smearing tells us precisely and quantitatively how much ionized matter sits between here and there. The missing baryons are in the cosmic web. The filaments are filled with hot, ionized plasma. The census is, to a first approximation, closed. What remains is not the question of whether the WHM exists. That question has an answer now. What remains is the question of its properties, its temperature distribution, its density profile, its behavior across cosmic time. The questions that require not a dispersion measurement integrated over a sightline, but a direct look at the gas itself, image of the filaments, a spectrum of the plasma. Those observations exist now too, or are beginning to. They came from a different instrument, one pointed not at a millisecond flash, but at the steady X-ray glow of the sky itself, scanning the entire observable universe one strip at a time. There is a particular kind of scientific patience that doesn't get discussed much. Not the patience of waiting for a result, though that exists too, but the patience of building toward one through accumulation rather than discovery. The patience of knowing that no single observation will be sufficient, that the signal you are looking for is distributed across too large a volume and too faint in any individual location to be seen directly, and that the only path forward is to add, to stack, to combine many weak measurements into one measurement that is strong enough to mean something. This is how eROSITA found the WHIM, not by pointing at a specific filament and seeing it glow, not by catching a lucky sightline through dense WHIM, gaseous, and resolving its spectrum, but by covering the entire X-ray sky, all of it, in 4 successive all-sky scans, and then combining the signal from nearly 8,000 individual filaments until the cumulative emission rose above the noise. The Spectrum Röntgen Gamma spacecraft carrying the eROSITA instrument was launched in July 2019 into an orbit around the second Lagrange point, roughly 1.5 million kilometers from Earth in the direction away from the Sun. eROSITA, built by the Max Planck Institute for Extraterrestrial Physics in Germany, consists of 7 identical X-ray telescope modules, each with its own CCD detector, arranged to observe the same patch of sky simultaneously. The combined effective area and field of view were designed specifically to enable an all-sky X-ray survey of sensitivity substantially deeper than anything previously achieved. The instrument completed 4 full all-sky scans, designated ERAS-1 through ERAS-4, before operations were paused in early 2022. Those 4 scans represent the deepest all-sky X-ray survey ever conducted, covering the full sky in the energy band between 0.3 and 1.2 kilo-electron volts, the soft X-ray range where WHIM emission, if it exists at detectable levels, is predicted to appear. The survey was not built specifically to detect the WHIM. It was designed to find galaxy clusters, active galactic nuclei, X-ray binaries, diffuse emission from supernova remnants, and a range of other X-ray sources across the sky. The WHIM detection was a goal embedded within that broader program, one that required a dedicated analysis method rather than standard source detection algorithms. The analysis that produced the WHM detection used a technique called stacking. The principle is straightforward even if the implementation is not. If you have a large sample of objects, each too faint to detect individually, but each predicted to emit signal in roughly the same way, you can align them, overlay their sky positions, and add the emission from each location into a combined image or spectrum. The individual signals are too weak to distinguish from noise, but signal adds coherently while noise adds in quadrature, meaning noise grows more slowly than signal as you accumulate more observations. With enough objects, the combined signal-to-noise ratio rises to detectable levels, even when no individual detection was possible. The input sample for the eROSITA WHIM analysis was 7,817 cosmic filaments, identified from optical galaxy catalogues from the Sloan Digital Sky Survey. The filaments were identified by their galaxy overdensity, the statistical excess of galaxies along elongated regions of the sky compared to the surrounding field. Each filament was positioned, oriented, and added to the stacked dataset. Point sources, detected X-ray halos from resolved galaxy groups and clusters, active galactic nuclei identified in X-ray and optical catalogues, were masked before stacking to reduce contamination from sources unrelated to the filament gas itself. The stacked X-ray signal from the full sample of 7,817 filaments in the 0.3 to 1.2 kilo-electron volt band reached a significance of 9 sigma. This is, by any standard in observational astrophysics, a confident detection. 9 sigma means the probability of the signal arising from a statistical fluctuation in the background is vanishingly small, far below any conventional threshold for a claim of detection. But 9 sigma was the total X-ray signal from the filament regions. Not all of that signal is WHIM emission. The contamination question is the careful part of the analysis, and it is where the result becomes more nuanced without becoming less meaningful. Even after masking known point sources and resolved extended sources, some fraction of the X-ray signal in filament regions comes from unresolved sources, galaxies with active nuclei too faint to be individually identified and masked, X-ray binaries within filament galaxies, hot gas in the halos of individual galaxies that falls within the filament boundaries but is not the diffuse filamentary WHIM itself. These contributions cannot be masked without removing them from the catalogue entirely, which would bias the sample. The eROSITA analysis estimated this contamination fraction by comparing the signal profiles of filament regions with modelled contributions from unresolved sources using population statistics of known X-ray source types. The conclusion was an approximately 40% contamination fraction, meaning that roughly 40% of the 9 sigma total X-ray signal could be attributed to sources within filament galaxies rather than to the diffuse filamentary plasma between them. Subtracting this contamination fraction left a residual signal attributable to the WHIM itself, detected at a significance of 5.4 sigma, still well above the conventional 5 sigma threshold. A confident statistical detection of X-ray emission from the diffuse warm-hot intergalactic medium distributed across thousands of cosmic filaments, measured not through any individual filament but through their collective average. The spectral fitting of the stacked emission produced a temperature measurement. Fitting the combined spectrum with a single temperature thermal plasma model, the best fit temperature came out at 10 to the power of 6.84 Kelvin, with an uncertainty of plus or minus 0.07 in that exponent. 10 to the 6.84 is approximately 6.9 million Kelvin, just under 7 million degrees. This sits near the upper end of the WHIM temperature range, as defined by the simulations, which predict gas between 100,000 and 10 million Kelvin distributed across filaments, with the hotter gas concentrated in denser regions and near cluster outskirts. The eROSITA best fit temperature being near the upper boundary is expected, and the paper notes it explicitly, because X-ray emission in the 0.3 to 1.2 kilo electron volt band is produced preferentially by the hotter fraction of the WHIM. Cooler WHIM gas emits at lower energies and contributes less to this particular energy band. The single temperature fit is not a description of the full WHIM temperature distribution. It is the emission-weighted average of whatever fraction of the WHIM is hot enough to appear in the energy band eROSITA is sensitive to. The baryon density contrast of the detected gas, the ratio of local baryon density to the cosmic average, came out at 10 to the power of 1.88, which translates to roughly 76 times the cosmic average baryon density at the filament centers. This is in general agreement with cosmological simulations of filament structure, which predict over-densities in the range of 10 to 100 times the cosmic average in the denser parts of filaments, with the density falling off toward the filament edges. What eROSITA produced was not a picture of a single filament. It was a statistical measurement of the average emission properties of thousands of filaments, combined into a detection that no individual filament could have provided. The WHIM, too faint and too diffuse to see in any one place with current instruments, becomes visible when you add 8,000 places together. There is something slightly uncomfortable about that, and I'm not sure how to resolve it. A detection built from averages is still a detection. The physics it reflects is real. The signal is consistent with simulations, consistent with the FRB baryon measurements, consistent with the temperature range predicted by shock heating models. But it is a statistical object, not an image. It tells you about the population of WHIM-bearing filaments on average, not about any individual filament in particular. That individual filament, the direct spectroscopic detection of a single strand of the cosmic web, came separately from a different instrument, pointed at a specific region of sky where conditions happen to be favourable for exactly the kind of observation that stacking cannot provide. The Shapley supercluster sits about 650 million light-years from Earth, in the direction of the constellation Centaurus. It is the most massive concentration of galaxies in the nearby universe, a region where dozens of galaxy clusters and hundreds of groups are packed into a volume that is, by cosmic standards, unusually dense. The gravity of that concentration is significant enough to exert a measurable pull on the motion of the local group, a small cluster of galaxies that includes the Milky Way and Andromeda. The entire local group is moving toward Shapley slowly, carried along by the gravitational attraction of something hundreds of millions of light-years away. Inside the Shapley supercluster, as in any dense region of the cosmic web, Filaments connect the clusters to each other. Gas flows along those filaments. Dark matter concentrates along their spines. Galaxies cluster near their axes. The whole structure is woven together by the same gravitational dynamics that shaped every other part of the cosmic web, just more so, more concentrated, more active, more massive per unit volume than most regions of the observable universe. In 2024, a team of astronomers identified something inside the Shapley supercluster using optical galaxy data. A filament, a new one not previously catalogued, connecting two pairs of galaxy clusters, the A3532 and a 3530 pair at one end, and the A3528N and A3528 pair at the other. The filament's length, measured along its axis, was approximately 7.2 megaparsecs, about 23 million light-years. Its inclination to the plane of the sky was roughly 53 degrees, meaning it was angled toward us rather than lying flat across our field of view, which complicated the geometry but did not prevent analysis. What happened next was not automatic. Finding a filament in optical galaxy data is one thing. Detecting the gas inside it, the actual warm, hot plasma that the filament contains, is different in kind, not just in difficulty. The optical detection tells you where the galaxies are. The gas detection tells you what fills the space between them. And detecting the gas requires X-ray observations because the WHIM at filament temperatures emits in the soft X-ray band. The team obtained X-ray data from two instruments. XMM Newton, the European Space Agency's large X-ray observatory, provided both imaging and spectroscopic data for the filament region. The combination of imaging analysis to establish the spatial extent and morphology of the emission, and spectroscopic analysis to measure the temperature and density of the emitting gas, is what distinguishes this detection from a stacking result. Stacking gives you population averages. Spectroscopy gives you the properties of a specific object. The imaging analysis confirmed excess X-ray emission along the filament axis. Extended emission not associated with the cluster pairs at the filament's ends, but distributed along the connecting strand between them. The emission was faint, not dramatic, not the kind of signal that jumps out of a raw image. It required careful subtraction of the cluster emission at the filament's ends, subtraction of background sources, and correction for the telescope's instrumental response before the filament's own contribution became insoluble. The spectroscopic analysis was the harder part and the part that matters most for what the detection actually tells us. Extracting a spectrum from diffuse, faint, extended emission in an X-ray observation is a different challenge from extracting a spectrum from a point source. A point source, a quasar or a bright X-ray binary, concentrates its photons in a small region of the detector. The spectrum is clean. For extended emission spread across a large region of sky, the photons from the source compete with photons from the background, from unresolved point sources within the extraction region, from hot gassing galaxies that happen to sit along the line of sight, from the instrument's own detector noise. All of these must be characterized and subtracted, and the accuracy of the subtraction sets the reliability of what remains. The Shapley Filament analysis addressed this through what the authors described as a sophisticated spectroscopic method designed to account for all forms of residual emission unrelated to the filament gas itself. Unresolved active galactic nuclei within the filament volume were modelled statistically. Galactic halo emission from individual filament galaxies was estimated and subtracted. The cosmic X-ray background was measured from regions adjacent to the filament and used to constrain the background contribution within the filament extraction region. The density derived from the spectral fitting was approximately 10 to the minus 4 particles per cubic centimetre, which is 10 to the minus 4 per cubic centimetre, or about 100 particles per cubic metre. This is at the denser end of the WHIM range, which is expected for a filament in a region as overdense as the Shapley supercluster. The gas mass enclosed within the filament volume, estimated by combining the density with a cylindrical geometry approximating the filament's shape, was substantial. The gas fraction, the ratio of gas mass to the total mass inferred from other methods, came out somewhere between 5 and 15% depending on the mass reconstruction approach used. Within the range of what simulations predict for filamentary gas fractions, the emission showed no strong trend in intensity within 375 kiloparsecs of the filament central axis, consistent with the expectation that filament density profiles only begin to fall noticeably at larger radii from the spine. What this detection represents is a specific kind of knowledge, not a statistical average over thousands of filaments, not an inference from dispersion measures integrated along a sightline, not a marginal absorption feature at the edge of instrumental sensitivity, a single filament, imaged, spectrally characterized, temperature measured, density measured, gas mass estimated, the WHIM in one specific strand of the cosmic web, identified, observed and described. I find something quieter about this than I expected to. The detection of a thing that was always supposed to be there, confirmed by careful subtraction of everything that isn't it, produces a result that is less dramatic in tone than the decades of effort to reach it. The filament was there, the gas was there, the temperature is what the model said it would be. The density is in the predicted range, everything fits, which is not nothing, that things fit, that the physical picture assembled from simulations and in direct measurements and marginal detections over 30 years produces a specific filament with a specific temperature and a specific density that all agree with each other, is itself a kind of confirmation that the picture was right. The Shapley filament is 23 million light-years long, 2 million Kelvin, and roughly as dense as the simulations expected. It connects 4 galaxy clusters in the most massive nearby supercluster in the observable universe, and until very recently it was completely invisible. A Mach number is a ratio, nothing more than that, at first. The speed of something divided by the speed of sound in the medium it's moving through. Mach 1 means the two speeds are equal. Mach 2 means the object, or the flow, is moving at twice the local speed of sound. Mach 10 means 10 times. The number encodes something specific about what happens at a shock. The higher the Mach number, the more abruptly conditions change at the shock boundary, and the more efficiently the kinetic energy of the flow gets converted into thermal energy on the other side. A weak shock, Mach 2 or 3, converts a modest fraction of the infall energy into heat. A strong shock, Mach 10 or 100, converts nearly all of it. The relationship between Mach number and post-shock temperature is not linear. It is quadratic. The temperature downstream of a strong shock scales with the square of the infall velocity, and since the Mach number tracks the infall velocity relative to the sound speed, a shock at Mach 10 heats the gas dramatically more than a shock at Mach 3, even though the numerical difference sounds manageable. This is why Mach numbers matter for the WHIM. The range of Mach numbers found in cosmological shocks spans several orders of magnitude, and the consequences of that range for gas temperature are correspondingly large. Cosmological shocks fall into 2 broad categories, not rigid ones. The boundaries between them are physical rather than administrative, defined by where the shocks occur and what gas they are processing. External accretion shocks form at the outermost boundaries of large-scale structure, at the edges of filaments, at the peripheries of galaxy clusters, at the surfaces where the large-scale gravitational potential wells of cosmic structure meet the surrounding medium. These are the shocks that process gas falling in from the voids, gas that has never previously encountered a shock of any kind. Cold gas, at temperatures of 10,000 Kelvin or so, the floor set by the photoionizing ultraviolet background that fills the universe after reionization. That gas falls along the gravitational gradients of the cosmic web, accelerates over enormous distances, and eventually reaches the outer boundary of a filament or cluster. The sound speed of that cold, diffuse, pre-shock gas is low, perhaps tens of kilometers per second. The infall velocity of the gas, built up over hundreds of millions of years of gravitational acceleration, can reach hundreds of kilometers per second at the boundary of a massive cluster. The ratio, the Mach number, can be 10, 50, 100, occasionally higher. External accretion shocks, the shocks that produce most of the WHIM heating, routinely operate in the range of Mach 10 to Mach 1000 at the edges of large-scale structure. These are strong shocks. The conversion of kinetic energy to thermal energy at these boundaries is efficient. The gas that comes through them is hot. Genuinely hot, in the range of millions of Kelvin, because the infall velocities are large and the pre-shock sound speed is small and the ratio of those two numbers is large. Internal merger shocks are different in almost every respect. They form inside structures that have already been shock heated, inside galaxy clusters, where two subclusters are merging, where the gas of one cluster rams into the gas of another at relative velocities of a few hundred to 1,000 kilometers per second. But the medium these shocks are moving through is not cold, diffuse, pristine void gas. It is already hot. Intracluster gas sits at tens of millions of Kelvin. The sound speed in that gas is high, hundreds of kilometers per second. When two clusters merge, the relative velocity of the gas flows is not much larger than the sound speed of the medium itself. The Mach numbers of internal merger shocks typically run between 2 and 4, sometimes reaching 5 or 6 in particularly energetic mergers. These are weak to moderate shocks by the standards of what Mach numbers can reach. They convert a smaller fraction of the kinetic energy of the merger into additional thermal energy. The gas they process is already hot, so the fractional temperature increase from crossing one of these shocks is modest. What internal merger shocks do produce is a lot of total energy, because galaxy cluster mergers involve enormous masses moving at high velocities, and even a modest conversion efficiency applied to that kinetic energy budget yields a significant thermal contribution. Cluster mergers are, by total energy release, among the most energetic events in the universe since the Big Bang. The shocks they drive are responsible for the observed radio relics, diffuse radio-emitting structures found at the outskirts of merging clusters, produced by cosmic ray electrons accelerated at the shock boundary. But they are not the shocks responsible for the WHIM. The WHIM exists because of the external accretion shocks, the Mach hundreds at the filament edges, the boundaries where cold void gas crosses into the heated filamentary medium for the first time irreversibly. That first crossing is something worth considering on its own terms. Gas that formed in the early universe, that drifted through the expanding cosmos for billions of years in a relatively undisturbed state, photoionized but cool, thinly spread through the large-scale structure's gravitational gradients, accumulating speed as it fell, and then hitting the outer boundary of a filament at velocities that dwarf the local sound speed by factors of 10, 50, 100. The crossing is not gradual. The boundary is not diffuse, not a gentle transition zone. It is a shock front, thin in the physical sense, a surface across which temperature jumps by orders of magnitude in a distance that is, in cosmological terms, essentially zero. Cold on one side, hot on the other, the Mach number at that boundary encodes the entire history of the gas's fall, the depth of the gravitational well it descended, the distance it travelled, the speed it accumulated. All of that history converts at the shock boundary into temperature, and it converts once. The pristine gas that crosses an external accretion shock is no longer pristine after. It has been thermalized. It becomes part of the WHIM. Its first shock is its initiation into the hot medium that fills the filament, and subsequent shocks, if it encounters them as it continues falling toward the cluster core, are internal shocks operating in an already hot medium at lower Mach numbers. The spatial distribution of shock Mach numbers in cosmological simulations is, in this sense, a map of the heating history of the universe's gas. High Mach numbers at the outermost edges of structure, where the pristine gas is crossing in. lower Mach numbers deeper inside where the gas has already been processed. The WHIM's temperature gradient from filament edge to cluster core traces this Mach number distribution. Cooler at the periphery where the shocks are strong, but the gas is just arriving. Hotter toward the denser regions where accumulated heating and compression have had more time to act. The universe has been running accretion shocks at these Mach numbers for most of its history. Every filament edge, every cluster outskirt, a boundary where cold falls into hot and comes out different. The cumulative product of all those crossings, across all those boundaries, across billions of years, is the WHIM, a ratio, speed over sound speed. The Mach number is just a ratio, but what it encodes at Mach 100 at the edge of a cosmic filament is the thermal fate of half the ordinary matter in the observable universe. There is a supermassive black hole at the centre of the Milky Way. It is called Sagittarius A star, and it is currently quiet, not dormant in any deep sense, just not actively accreting large amounts of material at the moment, not producing the kind of outflow that would make it visible from across the galaxy. It sits there, roughly 4 million solar masses of compacted space-time curvature, doing relatively little except curving the orbits of stars that pass within a few light hours of its event horizon. Most supermassive black holes in the nearby universe are like this, quiet. They grew mostly in the past, during periods when their host galaxies were younger and gas supplies were abundant, when material was falling into them at rates high enough to produce luminosities that outshone entire galaxies. Those periods are called active phases. The galaxies hosting black holes in active phases are called active galactic nuclei, AGN. The AGN phase is not permanent. It ends when the black hole has consumed or expelled enough of the surrounding gas to starve itself, or when the host galaxy's gas supply runs out for other reasons. What remains afterward is a quiet black hole in a galaxy that has been profoundly changed by what the active phase did to it. The question this chapter is concerned with is how far those changes reach. When a supermassive black hole is actively accreting, the infalling material doesn't fall straight in. It forms a disk, an accretion disk, heated by friction and compression to temperatures that produce X-ray and ultraviolet radiation intense enough to ionize gas across enormous distances. A fraction of the infalling material, instead of crossing the event horizon, gets redirected into jets, collimated outflows of plasma moving at relativistic speeds along the black hole's rotation axis. The jets can extend, in the most extreme cases, for millions of light years beyond the host galaxy. The radio galaxy NGC 6185 has jets stretching roughly 7 megaparsecs, about 22 million light-years. These are not narrow, contained structures with consequences limited to their immediate surroundings. The jet deposits energy wherever it terminates and wherever it passes through. At its termination point, the jet's kinetic energy thermalizes, heating the surrounding gas and driving a bow shock outward into the intergalactic medium. Along its length, the jet inflates lobes of relativistic plasma, bubbles of low-density, high-pressure material that push outward against whatever medium surrounds them. The mechanical energy involved in this process is substantial. A typical powerful AGN jet carries kinetic energy at a rate of 10 to the 44 joules per second or more, sustained over timescales of tens to hundreds of millions of years. Integrating that energy output over the jet's active lifetime produces a total mechanical energy input to the surrounding medium that is genuinely large by any reasonable measure, including by the standards of the energetics already involved in gravitational shock heating. The conventional picture of AGN feedback situates its consequences primarily at the scale of the host galaxy and its immediate circumgalactic medium. The hot halo of gas surrounding a massive galaxy, the medium within a few hundred kiloparsecs of the galactic center, is clearly regulated by AGN activity. Observations of galaxy clusters show that the brightest central galaxy sitting at the cluster's gravitational center produces AGN outbursts that inflate cavities in the intracluster medium, drive weak shocks through the cluster gas, and deposit enough energy to offset the radiative cooling that would otherwise cause the intracluster gas to collapse onto the central galaxy. This is a GN feedback at the cluster scale, well established, well observed, understood in its broad outlines. What is less well established, and more relevant to the WHIM, is how far AGN energy reaches beyond the cluster, beyond the circumgalactic medium, into the filamentary intergalactic gas. The simulations address this, and the answer they tend to produce is that the reach is longer than the conventional picture suggests. Gas expelled from galaxies by AGN-driven winds doesn't stop at the virial radius of the host halo. It continues outward, carrying kinetic and thermal energy into the surrounding intergalactic medium. The expelled gas mixes with filamentary gas. It drives weak shocks into material that may already have been processed by gravitational accretion shocks. It deposits metals, oxygen and carbon and iron produced in the galaxy's stars into gas that would otherwise be nearly pristine. This last point is not incidental. The WHIM's metallicity, the fraction of elements heavier than helium that it contains, is a tracer of how much AGN and supernova-driven outflow has reached it. The filament gas is not primordial. It carries a measurable, if modest, enrichment that could only have arrived from galaxies. The metals travelled. The energy that carried them travelled with them. The contribution of AGN feedback to WHIM heating is a second mechanism, not a primary one. Gravitational shock heating, the conversion of infill kinetic energy into thermal energy at accretion shocks, is the dominant process. The simulations are consistent on this. The energy budget of gravitational heating, integrated over cosmic time and over the volume of the cosmic web's filaments, substantially exceeds the energy input from AGN and supernova-driven winds combined. But substantially exceeds is not the same as renders negligible. The AGN contribution modifies the WHIM's temperature structure in regions where outflow energy is deposited. Near massive galaxies, near the most active AGN hosts, the intergalactic gas is warmer than it would be from gravitational heating alone. The AGN doesn't create the WHIM, it adjusts it, adds to the thermal budget in specific locations at specific cosmic times, with a spatial distribution that traces the history of black hole growth across the universe. That history has a shape. A GN activity peaked at a redshift of around 2, when the universe was roughly 3 billion years old, when star formation rates were highest and gas supplies most abundant. The black holes were growing fastest then. The jets were most active. The energy input to the surrounding medium was highest, and that energy deposited into the intergalactic medium at redshift 2 didn't disappear. It is still there, in the thermal state of the gas, in the slightly elevated temperatures of filament regions near where massive galaxies formed and grew. There is something worth sitting with in the idea that a black hole's growth, a process occurring in a region smaller than the solar system, can leave a thermal signature in gas that is millions of light years away. The jet that carries the energy is long, sometimes absurdly long, stretching across intergalactic distances. But even without a jet, the winds and outflows driven by AGN radiation can reach the circumgalactic medium and beyond, pushing gas outward, heating it, enriching it. The intergalactic medium carries the record of what happened inside galaxies. The AGN feedback that regulated star formation, that shaped the mass function of galaxies, that prevented the most massive halos from cooling and forming too many stars, also left marks in the gas between the galaxies. Slightly elevated temperatures in specific regions, metals where there shouldn't be metals. A thermal history written in the intergalactic plasma by processes that began, in each case, with a supermassive black hole and the gas that fell toward it. Gravity heats the WHIM through infall. A GN heat it through expulsion. The two mechanisms push from opposite directions, inward and outward, and the gas between the galaxies holds the record of both. The oldest light in the universe is still here. It left its source about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen for the first time, releasing the photons that had been trapped in the hot, opaque plasma of the early universe. Those photons have been travelling ever since, nearly 14 billion years, expanding with the universe, cooling as the universe expanded, losing energy to the growth of the space they move through. They arrive at every point in the universe from every direction simultaneously, a nearly uniform bath of microwave radiation at a temperature of 2.725 Kelvin. The cosmic microwave background, nearly uniform, not perfectly. The CMB has been measured with extraordinary precision across the full sky, first by the COBE satellite, then WMAP, then Planck, and the temperature variations that pattern it, the anisotropies, carry encoded information about the early universe's density fluctuations, the seeds of everything that followed. Those anisotropies are small, 1 part in 100,000, and their pattern is the subject of most CMB cosmology. But the CMB photons, after they were released, did not travel to us through nothing. They passed through the universe as it formed, through galaxy clusters, through filaments, through the warm, hot intergalactic medium, and some fraction of them passing through regions containing hot ionized gas were scattered by free electrons in that gas, scattered in a specific way with a specific consequence for their energy that leaves a measurable mark on the temperature map of the CMB. The process is called the thermal Sunyaev-Zel'dovich effect, named for the two Soviet astrophysicists, Rashid Sunyaev and Yakov Zel'dovich, who described it theoretically in 1972. The physics is inverse Compton scattering. A CMB photon with energy corresponding to a temperature of 2.725 Kelvin passes through a region containing hot electrons. The electrons, at temperatures of millions of Kelvin, are moving fast. When a CMB photon scatters off one of those electrons, the photon gains energy from the electron, not a dramatic exchange. Each individual scattering event transfers a tiny fraction of the electron's kinetic energy to the photon, but the effect is systematic. CMB photons passing through a hot gas consistently gain energy. The photons that come out the other side have, on average, slightly higher energies than the ones that went in. Higher energy means the photons appear to come from a slightly hotter region than the true CMB temperature. In the direction of a hot gas cloud, the CMB temperature appears slightly elevated at high frequencies and slightly reduced at low frequencies, because the scattering shifts photons from lower to higher energies, redistributing them across the frequency spectrum in a way that is spectrally distinct from any other CMB signal. This spectral signature, the specific frequency dependence of the TSZ effect, is what allows it to be separated from other contributions to the CMB temperature map. The amplitude of the effect is quantified by the Compton mu parameter, an integral of the electron pressure along the line of sight through the gas. High electron pressure, meaning hot and dense gas, produces a large Y parameter and a strong TSZ signal. Low electron pressure, meaning cool or diffuse gas, produces a small Y parameter and a weak signal. The WHIM in filaments has low electron pressure by the standards of galaxy clusters because it is diffuse, because its density is low even where its temperature is high. The signal it produces in the CMB is faint but not zero, and faint with enough averaging becomes detectable. The de Graaf 2019 study approached the problem of filamentary TSZ detection the same way the eROSITA study would later approach WHIM X-ray emission, through stacking. Rather than attempting to detect the TSZ signal from a single filament, which would require a signal far above what current CMB experiments can resolve, the study stacked the Planck satellite's Compton Y parameter map at the positions of over 1 million galaxy pairs drawn from the CMASS galaxy catalogue of the Sloan Digital Sky Survey. The logic of the sample selection is worth understanding. The CMASS catalogue contains massive galaxies at redshifts between roughly 0.4 and 0.7, selected to trace the large-scale structure at those distances. Galaxy pairs, 2 CMA-SS galaxies, separated by a projected distance and a line-of-sight velocity consistent with being connected by a filament rather than simply being nearby by chance, are probable filament endpoints. The space between them is probable filament volume. By stacking the Y-parameter map at the midpoints between over 1 million such pairs, each pair contributing a small signal from whatever gas connects them, the study accumulated enough detections to build a statistical measurement of the average filamentary TSZ signal. The halos of the galaxies themselves contribute a TSZ signal, because every massive galaxy has a hot gaseous halo. This contribution had to be modelled and subtracted. The study assumed spherical symmetry for the halo contributions, modelling each galaxy's TSZ profile and removing it from the stack signal, leaving a residual that should reflect only the gas in the connecting region between the galaxy pairs, the putative filament. The residual TSZ signal after halo subtraction was detected at a significance of 2.9 sigma. This is below the conventional 5 sigma threshold for a confident detection. It sits in the territory of a probable signal rather than a confirmed one, with a meaningful probability, perhaps a few percent, that it could arise from imperfect halo modelling or a statistical fluctuation in the background. What the 2.9 sigma signal means physically, if it is real, is that the gas between those galaxy pairs is hot enough and dense enough to scatter CMB photons measurably. The Compton Y-parameter magnitude recovered from the stack signal, 0.6 plus or minus 0.2 times 10 to the minus 8, is consistent with gas at WHIM temperatures filling a filament of roughly 10 megaparsecs in length. The study estimated that bound gas in the galaxy halos could contribute at most 20% of the measured signal, meaning the majority of the TSZ excess, if it is real, comes from diffuse intergalactic gas rather than from gas associated with the galaxies themselves. The significance was, and remains, marginal. Whether it will be confirmed at higher significance by future CMB experiments with better resolution and sensitivity is an open question. The Atacama Cosmology Telescope and the South Pole Telescope have both produced CMB maps with higher resolution than Planck, and cross-correlations of those maps with galaxy filament catalogues represent a natural extension of the de Graaf approach. But the marginal detection, taken alongside the FRB baryon measurements and the eROSITA X-ray results and the O6 ultraviolet detections, fits into a coherent picture. The CMB photons that have been travelling since the universe was 380,000 years old are being scattered slightly by the WHM. The oldest light in the universe carries faintly the imprint of the hottest ordinary gas in the universe. The photons that left before any filament existed, before any galaxy formed, are arriving at our detectors having passed through the thing this entire video has been about. There is something almost circular in that. The oldest signal in the universe marked by the newest structures, the imprint is faint, but it is there, or it seems to be, and what it would mean if confirmed is that the WHIM leaves its mark on everything that passes through it, including light that has been travelling for nearly 14 billion years. Every instrument currently capable of detecting the WHIM is doing so at the edge of its sensitivity. The eROSITA All-Sky Survey required stacking nearly 8,000 filaments to pull a 5.4 sigma signal from the background. The XMM Newton detection of O7 absorption along the 1ES1553+113 sightline sat at a significance most of the community considers marginal. The Planck TSZ filament signal reached 2.9 sigma. The tools available right now are producing results, real results, meaningful results, but they are doing so at the limit of what they were built to do, in some cases beyond the limit of what they were designed for. The next generation of X-ray observatories was designed with the WHIM specifically in mind, not as a secondary target, as a primary scientific objective. NewAthena, the reformulated version of the European Space Agency's Athena mission, the Advanced Telescope for High-Energy Astrophysics, is the instrument built to close the questions that current observations have opened without fully answering. Its launch, currently scheduled for the early 2030s, is still years away. The telescope does not yet exist in flight form, but the instrument it will carry, the X-ray Integral Field Unit, has been designed with a specific and concrete sensitivity goal that addresses directly the measurement problems that have made WHIM detection so difficult. The XIFU is a microcalorimeter, not a grating spectrometer like the ones on Chandra and XMM Newton that have been used for WHIM absorption searches. The distinction matters physically. A grating spectrometer disperses X-ray light by wavelength, spreading it across a detector, the way a prism spreads visible light into a rainbow. The resolution it achieves depends on the grating geometry and the detector size. It works well for bright point sources with enough photons to fill the dispersed spectrum. It works poorly for faint sources, where the dispersed photons are spread too thin to build a useful spectrum in any reasonable observation time. A microcalorimeter works differently. Each incoming X-ray photon is absorbed by a tiny detector element, a transition edge sensor operating at temperatures close to absolute zero. The photon's energy heats the sensor by a measurable amount, and because the sensor is at a temperature where its resistance changes steeply with temperature, that tiny heat pulse produces a measurable electrical signal. The energy of each individual photon is measured directly, one photon at a time, without dispersion. The spectral resolution this produces is not limited by grating geometry. It is limited by how precisely the heat pulse can be measured, which for transition edge sensors at millikelvin temperatures is very precisely indeed. The XYFU will achieve a spectral resolution of 2.5 electron volts full width at half maximum across the energy range from 0.2 to 12 kilo electron volts. At the wavelengths of 07 and 08 absorption, the lines relevant to WHIM detection, this resolution is sufficient to resolve not just the presence of an absorption feature, but its profile, its width, its redshift, and potentially its velocity structure, and it achieves this across a field of view 5 arc-minutes in diameter, meaning it can study extended sources as well as point sources, something grating spectrometers cannot easily do. The effective collecting area of NewAthena's mirror at 1 kilo electron volt is approximately 1 square meter. Chandra's effective area at the same energy is roughly a tenth of that. The combination of higher sensitivity and higher spectral resolution means NewAthena will detect WHIM absorption features that current instruments cannot see, either because the features are too weak or because the spectral resolution is insufficient to separate them from the background continuum. The scientific goal for WHIM detection with NewAthena is to map the warm-hot intergalactic medium in absorption out to a redshift of approximately 1. Redshift 1 corresponds to a look-back time of roughly 8 billion years, meaning the universe was about 6 billion years old when the light we would be studying was emitted. The WHIM at that epoch was different from the WHIM today. The filaments were denser, the universe was more compact, the rate of structure formation was higher, and the relationship between AGN activity and gas heating was different in ways that current observations cannot fully constrain. Mapping WHIM absorption to redshift 1 means sampling the intergalactic medium at multiple points in cosmic time along each sightline, building a picture not just of where the WHIM is today, but of how it evolved. The temperature structure of the filaments at redshift 1 compared to redshift 0 encodes the history of shock heating across 8 billion years. The metallicity of the gas at those redshifts encodes the history of AGN and supernova-driven outflows reaching the intergalactic medium. The column densities of 07 and 08 absorbers at different redshifts constrain the ionization state of the gas and its density evolution as the universe expanded. These are measurements that current observations can gesture toward but not make precisely. The FRB dispersion measures give the total electron content without temperature. The eROSITA stacking gives an emission-weighted temperature average without spatial resolution of individual filaments. The marginal X-ray absorption detections give sightline column densities without the statistical sample to study evolution. NewAthena's XYFU, with its sensitivity and resolution, is designed to produce a catalogue of hundreds of confirmed WHM absorbers at well-characterized redshifts with measured column densities, temperatures derived from ionization modeling, and velocity information from line widths. The simulation groups that have been predicting WHIM properties for 30 years will have finally a data set large enough to test their predictions in detail rather than in outline. There is a specific prediction worth naming, because it illustrates what the measurement will actually constrain. Cosmological simulations of WHM evolution predict that the fraction of baryons in the warm-hot phase increases over cosmic time from a smaller fraction at high redshift to the 40 to 50% observed today. The increase happens because structure formation proceeds over time, generating more shocks as more gas falls into more filaments. At redshift 1, the simulation prediction is that a somewhat smaller fraction of baryons should be in the WHIM with a somewhat lower average temperature. Whether this is actually true is not something current observations can verify. The absorber sample is too small, the detection's too marginal, the uncertainty's too large. NewAthena should produce enough absorbers at enough redshifts to test this prediction statistically, to check whether the growth of the WHIM fraction across cosmic time matches what the lambda CDM model and its associated hydrodynamical simulations expect. If it does, it would be a confirmation not just of the WHIM's properties, but of the entire picture of structure formation that the missing baryon problem has been embedded in. If it doesn't, if the evolution doesn't match, that mismatch would point towards something in the physics of gas heating, or AGN feedback, or the large-scale structure itself that current models are getting wrong. Either outcome tells us something. That is what well-designed instruments do. They don't just confirm, they constrain, they produce measurements specific enough that the answer, whatever it is, narrows the space of possible pictures of how the universe works. NewAthena is, in this sense, not a telescope pointed at a known thing to study its details. It is a telescope pointed at a question that has been partially answered by instruments that were not quite sensitive enough to answer it fully. The question is, how did the intergalactic medium become what it is, and when, and through what sequence of processes? The answer is in the absorbers. The absorbers are in the filaments, and the filaments finally are within reach of being read. The universe is cooling down, has been, since the first fraction of a second after the Big Bang, when temperatures were so high that the distinction between matter and energy was not yet meaningful, when the density of the early cosmos was such that every point in space was indistinguishable from every other point, when the universe was, in the most literal sense, a single undifferentiated thing at unimaginable temperature. It has been cooling since then, expanding, thinning, losing energy to the growth of the space it occupies. The cosmic microwave background sits at 2.725 Kelvin now, and it will be colder still in 1 billion years, colder in 10 billion, trending toward the thermal death that cosmology has been predicting since the 19th century, when the implications of the second law of thermodynamics were first being worked out in full. Everything runs down, everything disperses. The universe moves, on average, from concentrated and hot to diffuse and cold, and yet the space between galaxies is searing. The filaments that thread the cosmic web are filled with plasma at temperatures between 100,000 and 10 million Kelvin. The gas that drifts between the largest structures in the observable universe is hotter than the outer atmosphere of the Sun, hotter than most things we would conventionally describe as hot, hotter than the surfaces of most stars. In an expanding and cooling universe, this is the condition of roughly half of all the ordinary matter that exists. The question worth sitting with, at the end of all of this, is why? The answer is gravity. But the answer being gravity is not as simple as it sounds, because gravity doing this requires something specific to be true about how gravity operates in an expanding universe, and that something is not obvious. The universe expands. Everything in it, on the largest scales, moves apart from everything else. The space between galaxy clusters grows. The space between filaments grows. The voids, those enormous underdense regions that make up 80% of the universe's volume, are getting larger. The universe is not just cooling on average, it is also, in a very real sense, diluting itself. But gravity is not average, gravity is local. In regions where matter is denser than the cosmic average, gravity wins against the expansion. Not permanently, not everywhere, but in specific locations and at specific scales, the gravitational attraction between matter exceeds the tendency of expansion to pull things apart. Matter in those regions stops moving with the expansion. It turns around. It falls inward toward the overdense region, accumulating, concentrating, building the filaments and clusters and walls of the cosmic web. This local reversal of the expansion is where the heat comes from, not from any external source, not from a furnace or a reaction, or a field injecting energy into the medium, from the simple fact that matter concentrated by gravity carries potential energy, and potential energy released through gravitational collapse becomes kinetic energy, and kinetic energy thermalized at a shock boundary becomes heat. The universe is cooling, and inside that cooling universe, gravity is running a local countercurrent, concentrating matter and converting the energy of that concentration into thermal energy, heating the gas in the filaments even as the background temperature of the cosmos falls toward its long-term floor. There is a timescale mismatch in this that I find difficult to hold clearly, and I'm not sure I ever fully resolve it. The cosmic microwave background will be at 1 Kelvin in about 3 billion years, at 1/10 of a Kelvin in 30 billion. The universe's average temperature is falling, will keep falling, is committed to falling, and simultaneously right now the filaments of the cosmic web are sitting at millions of Kelvin and will continue to sit at millions of Kelvin for billions of years to come because the accretion shocks that heat them are still running. Gas is still falling, the cosmic web is still forming structure on the largest scales, even as it expands. These two trends are not in contradiction. They operate on different scales. The expansion cools the universe in aggregate. Gravity heats specific regions locally. Both are real, both are happening simultaneously. The universe contains, at the same moment in cosmic time, gas at 2.725 Kelvin in the voids and gas at 10 million Kelvin in the filaments, separated by distances of tens of millions of light years, connected by the same large-scale gravitational structure. If you enjoyed this video, consider supporting us on Patreon, the link is in the description. What ordinary thermodynamics would predict without gravity is a universe where the temperature difference between the voids and the filaments gradually equalized, where energy flowed from hot to cold and the whole medium settled toward a uniform temperature. Gravity prevents this. Gravity keeps feeding energy into the filaments, keeps shocking new gas, keeps maintaining the temperature differential. The WHIM is hot, not because it was heated once and retained the heat, but because it is being continuously heated by ongoing accretion. The process is not finished. The cosmic web is not a relic. It is an active structure. The gas that is hot right now between the galaxies was cold before it fell. It was cold for billions of years, drifting through the expanding universe in a diffuse, nearly uniform state, slightly cooler than the CMB floor, barely interacting with anything. Then gravity pulled it toward an overdensity. It fell. It accelerated. It crossed a shock boundary. It thermalized. The transformation from cold drifting gas to hot plasma at millions of Kelvin happened, in each case at a shock front. A boundary thinner than anything you could draw, thinner than the mean free path of the particles crossing it, across which conditions change discontinuously. Cold on one side, hot on the other. The energy was always there, stored in the height of the gravitational well the gas hadn't yet fallen down. The shock converted it, instantly, efficiently, without remainder. All the heat in the WHIM is, in this sense, stored gravitational potential energy. Energy that was locked into the arrangement of matter in the universe. The slight over-densities and under-densities that gravity amplified over billions of years finally released when the gas fell far enough and fast enough to shock. The heat is the debt, paid in thermal energy, that the structure of the universe always owed. This is the thing that the missing baryon problem was always pointing toward, even before anyone knew it. When the census came up short, when the baryons couldn't be found in galaxies or clusters or the cool diffuse medium, the answer was not that the matter had gone somewhere exotic. It had gone somewhere gravitational. It had followed the dark matter into the filaments. It had fallen. It had shocked. It had become hot and nearly invisible, sitting in the intergalactic medium at temperatures that made it hard to find with the tools built before anyone knew to look there. The matter was always there, always hot, always threaded through the larger structures in the observable universe, filling the filaments that connect every galaxy cluster to every other, occupying the space between the things we can see with the energy of the falls we cannot watch. You spend 16 chapters learning how something works, and then, at the end, the thing feels both explained and somehow larger than it did at the start. The WHIM is half the ordinary matter in the universe. It is hotter than the solar corona. It formed because gas fell and hit things and heated. The mechanism is clean. The physics is settled, in its broad outlines, more settled than it was 10 years ago, and will be more settled still in 10 years more. And yet the filaments of the cosmic web, those enormous threads of hot plasma stretching across hundreds of millions of light years, connecting galaxy clusters across distances that take like billions of years to cross, are sitting there right now between the galaxies at millions of Kelvin in the dark. The universe is cooling down. Gravity keeps finding ways to push back.